All right, folks. So today we're going to look about analyzing and then writing a linear system of inequality. Okay. So first thing I'm going to say is, if you have not looked at how to graph them, you might want to go look at that first. If not, that's okay. You can actually do this first and then go back and look at the other one, but it'll help to know how to do this. Okay. So the first thing I'm going to show you is this. When we look at analyzing a linear system, so what we're looking for is the solution region, which is the area where the graphing and the shading overlaps. Okay. So if you have two lines or two inequalities, there's going to be an area where the shading occurs, where the shading is going to overlap itself like this. Okay. Like this dark shaded right here. That's the solution region. That's the region we're going to be looking for. So basically what it says is any point in this darkened region is an actual solution, an answer. Okay. If you have a point that is on the solid line right here, then it's not part of the solution. It keeps focusing in on me. If you have a point that is on this dotted line right here, it's not part of the solution. And then depending on what the lines look like, the intersection point right here can or may not be. And in this case, because one of the lines is dotted, then the point of intersection right here is actually not part of the solution region either. Okay. That being said, there's also a possibility of what we call a no solution, because what happens is the shaded areas do not actually overlap each other. Okay. When that happens, we call this a no solution. For this to happen, your lines must be parallel to each other. Okay. And parallel, in case you're wondering, basically means you have to have the same slope for each one when you graph it. Okay. So what does the solution region actually mean? Okay. So I'm going to give you a scenario real fast, something that maybe right up your alley. Okay. So you have a math test, coincidence, right? And you have questions that are worth 5 points, and you have questions that are worth 6 points. Okay. You want to get an A, so you want to figure out what are the possibilities to get if you want to earn 90 points or more. So normally we would have an equation or inequality where it says like 5 points, some number of questions right, and 6 points at some number of questions right has to be greater than or equal to 90. Okay. So if you want to, you could guess and check and say, okay, well, let's just say I get 10 questions right for this, and I get 2 questions right for this. Okay. So 10 questions right, 2, 4, 6, 8, 10, and 2 questions. I'm sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that point right there is the point I'm looking at. Well, if I do that, then 10 times 5 plus 2 times 6, okay, means that I only have a 62. And that would not be, that point, that combination would not be enough to give me my 90. Okay. Then, I could figure out, well, what if I do, let's just say I study and I get 15 questions right. And let's just say I get 15 questions right of the 6 points. Well, again, if I do this plus 15, 6 times 15, and it says I get a 165. Now, obviously, you're not going to get a 165 on the test, but that would be a possible combination you could get because it works. Now, we don't have a second constraint here, what we call a constraint to say what is, but what we can figure out is what is the least amount of possible combinations to get a 90. Okay. So what we do is we say, okay, let's just say that I get all X right. Okay. That means I could figure out that if I have 90 points and I get all 5 points right, I need to get 18 questions right. So 18 questions right. Okay. If I have 6 points and I want to get a 90, then I need to make sure and I get 15 questions right. Okay. And what this does, it creates a constraint or a boundary, kind of like this. I'm going to just kind of draw a solid line for right now. I'm not explaining why I normally wouldn't do this. But what that does, it says this. That's the least amount of points or combinations you could have to get your 90 or better. Okay. I could have everywhere above this. And again, if I knew what the maximum grade was, I could figure out the rest of this, but since I don't know what the maximum grade is, I'm going to assume it's 100. I'm going to just worry about this. Basically saying, okay, I could pick any point combination in this area here, or even along this line to get my 90. So this line represents the 90. Anything above this 90 represents, like your 91s, 92s, 93s, 94, so on and so forth. Okay. So any combination in this solution region is a solution that will fit this particular setup. And that's what inequality is, and that's what the solution region actually means. Okay. That's one scenario. Okay. So at this point right here, like I showed you a minute ago, it's not part of the solution region because obviously if I picked it, I would only get a 62 and that would not work for what I want. Okay. Another possibility, and I went ahead and drew this out to kind of show you, is when you deal with, let's just say operations, productions, things like that, where you only have what we call a finite amount of resources. And so what you can create is a region that represents your possible combinations. Like in this case here, you only have 240 acres that you can plant. Okay. But you're going to plant 2 different crops. And then you only have a finite amount of labor hours that you can use on workers, because you have to pay them. If you go over 220 hours, it's going to cost you more to actually hire them and that they work for you. Okay. Also, you can't plant more than 240 acres. Therefore, you have to kind of figure out, well, what's, my best mix and match of my 2 crops in order to make money. And I'm not going to get into the whole maximization of things, but that's what this kind of represents is this area here, this blue line represents your maximum number of hours you can, labor hours. And this green line represents the amount of acreage you can use. So it's kind of like saying, well, I could invest all my acreage into one crop. That would kind of be this area right here. I could invest all my labor hours into one crop here, or I can do some kind of combination here. So anything in this point here would say, well, if I use this, if I use 200 acres at some number of labor hours, that's going to give me what I want. So obviously there's usually something else that goes with this, kind of like saying I can make $40 profit off of one crop and $30 profit off one other crop. So what would be the best investment? Okay. So anything in this shaded area here would be a possible solution. Of course, usually you want to maximize profit, but I'm not going to get into that. Okay. But that's what a solution region is. That's what it actually does. Okay. So if I have a solution region, then how do I know what my equations are that created that solution region? Well, when you look at this, and I'm going to try and zoom in on this to kind of give you a better idea what this looks like. If I can. Yeah, perfect. I want to make sure and write these in y equals mx plus b form. And I'm going to call this equation, we'll call this one equation 1, and we'll call this one equation 2. Okay. So in equation 1, what I notice is this. My y-intercept right here sits right here at -4. That's my b value. So right off the bat, I know this is going to be -4 for my b value. Okay, I'm going to write it right here so you can kind of see what I'm writing. Okay. And then my slope is this. Well, if I pick a second point, like this point right here, to get from this point to this point, I know that I have to go down 1 and I have to run over 2 to get to this point. Okay. And since I went down 1, that would be a -1 over 2x, because that's my slope, to get to that point. I also know this is going to be a y. So the question is, are we shading, what's the symbol going to show you right here? Well, again, if you use a test point, and I know this is shading down, any point in here was going to be a true point automatically. Now, in a memorization technique, what they probably say is, well, since we know that this is shaded below this line, then we know this is going to be less than or equal to, because this is a solid line, in terms of how it's shaded. Okay. Not a big fan of memorization techniques, but again, unless you sit here and work through the test points, it makes more sense to do this right here. Now, I will say if you do a test point, I will say this. If you take it, I'm going to write it right here. kind of like this. And you use the 0.00 again. It's my favorite point to use. Okay. Kind of like that. Then I know that 0 and -4, right? 0 is not part of the solution, which means that this has to be false for it to work. And for it to work, that means that this has to be less than for it to work. Okay. So that's why this less than or equal to is the way it is. That's how you would check it. Okay, that's one way to do it. So like in equation 2, again, I know that my y-intercept right here sits at 3. So I know right off the bat I'm going to have a 3 for my y-intercept. Then, well, that's going to be plus 3, by the way. I can pick a point from here to here. 1, 2, 3, 4, 5, 6 over 1, 2. That looks like it's 6 over 2, which happens to be 3. And again, if I use my test point, 0, 0, I want to make sure that 0 and 3, which is really what I'm checking, by the way. I want to make this false. So in order for this to be false, 0 has to be greater than. So that this would be greater than or equal to because it's a solid line. Okay. But again, if you memorize above and below, that's, to write these, that's perfectly fine. All right. Next one, and again, I'll do it again. So here, we're going to call this equation 1 and equation 2 again. So equation 1, I'm looking at a y-intercept that looks like 5, a plus 5. And then I have a slope of, it looks like up 1 over 2. So that's 1/2 x, y. And again, 0, so 0 and 5 has to be true. So 0 is less than 5, so this would be less than or equal to 5. Okay. Line 2, it looks like it's going to be at, ooh, that's a tricky one, -3. And again, if I pick this point, 1, 2, 3, 4, 5, 6, 7, 8, 9 over 2, it looks like. Make sure I did that right. 1, 2, 3, 4, 5, 6, 7, 8, 9 over 2. Yep, it's 9 over 2 x, y. And again, I want to make this true for -3. So that would have to be that it's greater than. So greater than or, nope, just greater than in this case. Because it is a dotted line this way. Okay. These are a little bit trickier to kind of show you how to do it because you just, in my opinion, have to kind of just know math. But anyway, so here's example 3. I'm going to pause it so you can try it and then go. All right, there it is. So my first line is at -7. It looks like I go up 10 over 5, which would be 2. And again, since I want it to be 0 and -7, but I want it to be false because 0 is not part of my solution, it looks like, then 0 has to be less than 7, so 0 is less than 7 like that. Okay. Second one starts at 2, which is right here. It looks like I go up 1 over 5, so 1 over 5. And again, 0 and 2, 0 is not part of my solution, so I want it to be false. So 0 has to be greater than, so therefore greater than or equal to. Solid line is greater than or equal to. Dotted was just less than. Okay. Last one. Try it. All right, last one. And again, 7, 7, 7 over 3. It was really 14 over 6, by the way, when I went from here to here, but it goes to 7 over 3. Now, this one here, I'm going to explain something to you why 0 is less than 7, even though I know that's true. And it is, because here's what you have to consider. Because this is shaded here, you have to also consider that all of this is actually shaded too. It's just not showing it that way. So this first one here has to actually be true to do that. Second one here, because it's shaded away from 0. So this one's kind of shaded towards 0. This one's shaded away. This one here actually has to be false. Hence the reason why these two are the symbols that they are. But again, if you don't understand that, if you at least memorize the fact that this is shaded below this line, then this is why this is less than, this is less than. So there it is. Okay. So that's solution regions and how you write and how you interpret solution regions, what they actually mean. Okay. So hopefully that helps, and we will see you around.